It's the Chicago area discovery that could shake the universe, or at least our understanding of it. And it's based upon the study of tiny subatomic particles called muons that are behaving in ways that appear to be at odds with the so-called standard model of physics. So how could this experiment at Fermilab in Batavia upend what we think we know about just about everything? Joining us is Chris Polly, experimental physicist at Fermilab and one of the lead researchers on this project. Chris Polly, thank you so much for being here.
Yeah, good to be here. Good to be here.
All right, so this work is making headlines around the world right now. First of all, we alluded to the standard model of physics. For the layperson, what is that?
You can think of the standard model of physics as sort of the universe broken down on its most fundamental scale. You know, as particle physicists, what we're really interested in are the basic ingredients of the universe at the very smallest scales. What are the particles that are involved? What are the fundamental forces that govern how those particles interact? You know, we're basically one step down from the periodic table of elements you learned about at another step, a little more fundamental. But the amazing thing, knowing even the things about these smallest scales, that information helps us understand the largest scales, all the way up to supernova explosions and how the universe evolved. So that's what we like to do.
Why are these experiments causing so much interest and delight among scientists around the world?
Oh, it's because the muon is an extremely interesting particle. We've known about it for quite some time. It's not the fact that it exists that is fundamentally interesting. It's that we use it to probe other basic laws of physics at Fermilab. And so the thing that's interesting about these muons, we make a very intense source of them at our particle accelerator at Fermilab, which is a Department of Energy laboratory right outside of the Chicago area. We make them in a particle accelerator because, you know, you can sort of think of them as electrons. They're very similar. They have the same charge, they have the same spin properties, but they're also different in some fundamental ways. They're 200 times more massive and they're unstable. They only live for about 2 millionths of a second. So we make intense bunches of these at the Fermilab Accelerator Complex by accelerating protons up to very high energy, smashing the target, and eventually we collect the muons that come from that process. So that's why we use the muon. The thing we're particularly interested in is called the magnetic moment of the muon. Because they're kind of like little spinning tops and they have charge, muons, like their cousins electrons, you can think of as having their own little internal magnetic field. They generate their own magnetic field just like a bar magnet. And so our goal of our experiment is to measure the strength of that bar magnet to very, very high precision. So why do we do that? The reason we're interested in it is not so much because of the muon itself, it's because of this very strange fact that in the universe, it turns out particles are never really alone. They're constantly surrounded by an entourage of other particles that blink into existence and disappear. They appear for just an instant, and this is happening all the time. So these particles that appear in the field of the muon actually change the strength of that magnetic field ever so slightly, because you can think of the internal magnet as being screened by all these other particles that appear. So the reason that's interesting is because we know from the fundamental laws of physics that all the particles we discovered so far in the universe can fluctuate in and out and change this internal magnetic strength of these muons. So by going out and measuring it very, very precisely, we can then calculate with similar precision what we expect based on all the known particles in the universe. And if what you find in an experiment differs from that calculation, then you have to wonder, are there other particles, are there other forces that are appearing that we haven't yet directly discovered?
So the muons, the behavior is different than what you expect it to be given the standard laws of physics. What are the ramifications then for our understanding of the universe in general?
Well, so this experiment is actually a follow-up experiment to one that was done about 20 years at Brookhaven National Laboratory. And in that experiment, they did something very similar. They stored muons and looked at how strong their magnetic field that they generate is. And they found that it differed. It differed from the expectation from the standard model prediction by a number we call, by an amount of 3 sigma. That's 3 standard deviations. What that means is that if you went out and ran the experiment 1,000 times, you might only expect to find something as strange as that, something as different about 3 in every 1,000 experiments. And so that difference has intrigued particle physicists for about 20 years because we've been wondering, was that a hint that there is, some sort of new cast of characters entering in the entourage, some new basic ingredients in the recipe of the universe. And so at Fermilab, what we've done now is we've repeated that experiment with higher statistics, which much more modern detector technologies, much more powerful computer simulations. And what we found is that result from 20 years from Brookhaven, we find a result that is in very good agreement with that. And so what that means is that the significance of this discrepancy has now grown from what it was when it was roughly 3 sigma in the Brookhaven era to what we would now call a 4.2 sigma standard deviation.
So this is a big deviation. This doesn't mean that there was a mistake in the study. This signifies that there's something undiscovered here.
Yeah, so the headline news here is that, this experiment has confirmed this Brookhaven experiment, and now that probability of that difference between the standard model prediction, the theoretical prediction, and the experiment, would only be expected to be by chance about 1 in 40,000 times. So now we know there really has to be something driving this difference between the theoretical prediction and the experiment. So there's sort of only 3 options there. Either the experiment can be wrong, which we don't think is likely now that we've done a whole follow-up experiment, a new experiment at Fermilab that's confirmed the old one. It could be that the standard model prediction, there's something we don't understand about the normal particles. And so that's a very active area of research with the theoreticians in the field. They continue to evaluate that, and they're very excited to look at all their calculations again with this result in hand. Of course, the interesting possibility is that difference, that 1 in 40,000 probability, is really because there's something new in the universe, something we haven't yet discovered. And we have some pretty good reasons to believe that there are other things in the universe. For instance, we look out and we can sort of weigh the mass of the universe around us, and we find that there's roughly 4 or 5 times more mass in the universe than we can explain with all the visible matter, the stars, the planets, the people. And so we don't know what that matter is or what it might be. It could be we're swimming through.
And that could get to the discussion of dark matter and dark energy, which, as I know, physicists and scientists still haven't really unlocked the mystery of that. And unfortunately, we can't do it on this show because that's all the time we have. But Chris Polly, thank you so much for joining us.
Oh, thanks.